In this video, we'll now talk about gravitational fields in space. While gravity gets weaker as you get farther from a planet, it never becomes zero. There is always some gravitational field present due to every planet, star, and moon in the universe. The local gravitational field is usually dominated by the nearby masses, since gravity gets weaker as the inverse square of the distance. The contribution of a planet to the local gravitational field can be calculated using the same equation we've been using. You just have to be careful about what the R is in the formula. The contribution of a planet to the local gravitational field can be calculated using the same equation we've been using. You just have to be careful about that R. If a location A, as seen here in the diagram, is at a height h above a planet which has a radius r, then that distance little r is going to be the radius of the planet, which you see here, plus the h. Okay? So GA becomes GM over r, the radius of the planet, plus the height above the surface, quantity squared. So using that information, determine the gravitational field of Earth at a height of 6.4 times 10 to the 6 meters, which is equal to 1 Earth radius. Earth's mass is 6 times 10 to the 24 kilograms, and its radius is 6.4 times 10 to the 6 meters. Okay, so now we're going to be a height of 6.4 times 10 to the 6 meters above the Earth's surface. Go ahead and pause the video now. Okay, so let's go ahead and take a look at the solution. The gravitational field is equal to Gm over r squared. R is going to be the radius of the Earth plus the height above it. Well, the radius of the Earth and the height above it are the same value. It's 6.4 times 10 to the 6 meters. So we're actually doubling the radius, which ends up giving us 1/4 of the original gravitational field. Or in other words, 2.45 meters per second squared. If you didn't get this answer, again, make sure that you're not using the times 10 button thing without the parentheses. So make sure you're nesting your parentheses carefully. Determine the gravitational field of the Earth at a height of 2.88 times 10 to the 8 meters above the surface. This is the height of the moon above the Earth. The Earth's mass, again, is 6 times 10 to the 24 kilograms, and its radius is 6.4 times 10 to the 6 meters. Go ahead and pause the video now. Okay, so let's see what the gravitational field is located at the moon. Okay, we take the radius of the Earth, which is 6.4 times 10 to the 6, plus the height from the surface of the Earth to where the moon is located, which is 2.88 times 10 to the 8 meters. We divide that into our gravitational constant times the mass of the Earth, and we should get 4.6 times 10 to the minus 3 meters per second squared. Notice that the gravitational field is not zero. So now let's talk about the International Space Station. The International Space Station, also known as the ISS, is a research facility, the on-orbit construction of which began in 1998. The space station is in a low Earth orbit and can actually be seen from the Earth with the naked eye, especially if you know where to look in the nighttime sky. Its orbit is at an altitude of approximately 350 kilometers above the surface of the Earth. It travels an average speed of 27,700 kilometers per hour. This means that the astronauts see 15 sunrises every day. So it goes pretty fast. The occupants of the space station appear to be weightless. They float. Determine the strength of the Earth's gravitational field acting on the astronauts in the ISS. The Earth's mass is 6 times 10 to the 24 kilograms. Its mass is 6.4 times 10 to the 6 meters. The ISS is located 350 kilometers above the surface. Don't forget, we need to convert the kilometers to meters, and that's going to be 350 times 10 to the 3 meters, or 3.5 times 10 to the 5 meters. Go ahead and pause the video now and solve for the gravitational field acting on the astronauts in the ISS. Okay, so let's take a look at the solution. Substituting in the height of the space station, which is 350 times 10 to the 3 meters. We're going to add that to the 6.4 times 10 to the 6 meters for the radius of the Earth. We we add them together, take the square, and divide that into g times m, the mass of the Earth. And notice that the gravitational field is 8.78 meters per second squared. This is nowhere near zero. Okay, so notice that this is pretty significant. 8.8 meters per second squared is only one less than on the surface of the Earth, which is 9.8. So this tells us that the reason they appear weightless is not because there's no gravitational field there. There certainly is. The reason they appear weightless is because the space station and the astronauts are falling around the Earth. So remember, they're being pulled inward with a circular motion force, the gravitational force, okay, but they're moving tangent to that acceleration. So the acceleration is 8.78, but they're moving tangent to that path. So instead of free falling straight down, they're free falling straight down, but they're also moving tangent to the Earth's surface. And that makes it appear weightless. So it'd sort of be like if you were in an elevator and the elevator cable snapped and you were to jump up in the air. You would appear to be weightless, even though you and the elevator are falling at the same rate. How does the gravitational field acting on the occupants in the ISS compare to that acting on you now? Go ahead and pause the video. Okay, so let's take a look at the answer. It's slightly less. In the next video, we'll talk about orbital motion.